All right, so I'm Noah, and my partners here are Miles and Nate, and we're here today to discuss some CPU, GPU, and TPU algorithm runtime costs. So here's a brief outline of what we'll be covering for the next few minutes. We'll start with going over our research questions, some background information about our project specifically, and then I'll go over some of the highlights we gleaned from work that was published about similar projects before ours. Next, we'll be going over some specifics and detailed information about each of the three processor types. After that, we'll talk about how we went about testing the runtimes of various algorithms on these processors. And then to wrap up, we're going to show some comparisons between each of the processors for various tasks. We're also going to talk about differences observed between each of the processors compared to themselves based on parameters like chunk size. So we know that dealing with large data sets can be very time consuming, even when we're working with very simple algorithms or models. When speaking about cloud computing specifically, time translates pretty directly to cost, although costs also vary depending on resources being used. We also know that certain processing architectures can far outperform CPUs under a variety of conditions. So in terms of this project, the other processing architectures being referred to are graphical processing units, GPUs, and Google's tensor processing units, TPUs. So our project had several main focuses regarding the differences between these processors. The first question we had was about whether or not advanced ones are always beneficial with large data sets based on runtime alone. So we know the GPUs and TPUs can far outperform CPUs for tasks that are very compute intensive, like training neural networks, or anything involving parallelism or complex matrix computations. With this being said, they're often thought of as being universally better just because of their prominence in recent data-intensive machine learning advances. So it can be very easy when facing a large data set, regardless of the actual computing task at hand, to think it's just better to throw a GPU or TPU architecture at your problem in order to get faster results. And this is especially the case when using resources like Google Colab, where you have access to these very easily, or cloud computing environments with freer academic credits. However, will using these advanced processors always be beneficial, even for applications with very simple computing tasks? Building on these ideas, we also wanted to explore the actual trade-offs when using one type of processor over the others. Even if some processors are marginally faster for certain tasks, is it always worth the bump in price they'll be experienced? So for some background about our project setup, we began our project by using Google Cloud virtual machines set up with CPU-only architectures, GPU-boosted architectures, and Google Cloud TPUs. So we completed a fair amount of baseline testing with the setup using SSH connections to run Jupyter Notebook cells through the virtual machines we created. Eventually, though, we ran into problems with a few of the algorithms we wanted to test on various instances. The problems mostly revolved around optimization dependencies that could not be resolved within the Google Cloud environment. While these did not ruin the project goal, they made it hard to have baseline comparisons for as many algorithms as we hoped for, because each of the algorithms need to be run in a similar fashion in order to keep benchmarking fair, and they needed to run for all three processors in order to make comparisons. At the same time, we were running low on educational credits and did not want to accidentally charge expensive TPU or GPU hours. So from here, we decided to try using Google Colab as a front end while connected to Google Cloud storage buckets on a back end. The data sets being used were far too large to simply load in a Google Colab instance, so the connection had to be made between the two systems. Once we were using Google Colab, though, we had far less control over the specifics of the machine instances we were using, but we still had access to the GPU and TPU runtimes, as well as the standard CPU runtimes and all the optimizations that came with them. So next, for our data, we used files from the Wikidumps website, which carries numerous copies of a variety of Wikipedia pages in XML format. On the right side of the screen here, you can see a small snippet of what some of these Wikidumps XML data formats files might look like in their raw form. Throughout the project, we worked with Wikidumps files of various sizes, ranging in general from about 5 gigabytes to 100 gigabytes. So one thing we noticed pretty early on was a general linearity for each processor compared with itself in terms of file size and processing time. So this meant that time comparisons or ratios between the processors did not vary much between them, depending on the file size at all. So whether the file size was 10 or 100 gigabytes. So for testing purposes, we chose to use files that were generally on 15 gigabytes in size in order to perform as much testing as we had hoped for, because it took too long to test as many things we wanted with much larger data files and 100 gigabytes of size. So finally, for the processing tasks we chose to test on each processor, we decided to use simple algorithms that would not strongly favor the GPU or TPU over the CPU. Because the data sets were far larger than the memory on the machines we were using, we had to stream chunks of Wikidumps data in, process them, and remove them from memory before proceeding on to the next. Originally, we made use of XML parsing libraries like eTree, but we quickly realized that these did not really give us the range of testing capabilities that we wanted, especially for differing chunk sizes and also issues with XML formatting as you chunk the data. So we created our own method of streaming that allowed us to specify how much data in bytes to let through at a time as sort of another step in our comparison process between architectures. So before, during, and after the project, we reviewed previous work completed for similar studies. And here we have some of the highlights gleaned from them. This is sort of a mixture of highlights and important information from all the sources, but are all cited at the end of the presentation. The first three processors is the CPU, which have low latency and large local memory capacity when compared to the other two. They also have low overhead and are good comparatively when retrieving data through a network or somewhere that's not local. This last point is very important to our project, where we're trying to stream data through a network in order to process it. So the next processor is GPU. They can perform orders of magnitude better than CPUs in certain cases. However, they have limited multitasking capabilities and a low memory, and can incur overhead when they're completing computations that are optimized. So kind of different from the CPU, GPUs are very quick when using local data, but they're easily outperformed by CPUs when they have to retrieve data from a distance, again, similar to our project. And finally, TPUs are designed to be capable of high throughput with large batch sizes. However, they're not very universal, requiring certain very specific packages to run. And they also incur overhead costs when embedded in software design. And similar to GPUs, when compared to TPUs, TPUs also have a low memory capacity, and they perform best with local data and do not perform as well with network data and retrieving data from distance.
So now I'll be going over some of the different differences between the hardware architectures. So we're going to start off with looking at the different architectures. Mainly, we have the TPU right in front of us. So TPUs are really optimized for MO workloads. So one library that can be used to help optimize them is TensorFlow, which we ended up using in our project. And one other note about the TPU is that the cost is typically very high, on the order of magnitude of 20 or 50 times more than CPUs, or and then so maybe 10 times more than a GPU. Going to look at GPUs now. GPUs are really intended to do work similar to TPUs in that they can process machine learning workloads very well. The reason for this is that they have lots of different cores that can process small pieces of data. And so this makes them optimal for more generally parallel processing workloads, and also graphics processing. It's actually in the name, graphics processing unit. Some good models to run on GPUs include custom models, and for size, we have medium to large batch sizes. And once again, a lot cheaper than the TPU, but a little bit more expensive than the CPU. So this might be a good middle range option for people looking for fast performance on parallel processing, but not necessarily wanting to spend that much on TPU. So now moving on to the CPU. So CPUs are really optimized for the use of one core. So if you have a simple model and you can run it on one core, it can run very quickly. And just to be clear, the diagram on the right doesn't represent the exact CPU that we use, but it does represent a more general outline of what a CPU might look like. So you see lots of caches, so there's lots of ability to draw from memory really very quickly, but a lower number of cores as compared to GPU and TPU. One way it might be limited though might be by network. So whereas other instances can draw from the network, the CPU might be limited. And just a quick note on the general setup of our hardware. Google Colab, due to its varying kind of ability or availability of GPUs, we weren't able to nail down specifically which GPU or instance that we had, but we know that it was generally likely to be a T4 instance from NVIDIA. And the CPU was likely a 1 or 2 core Intel Xeon processing unit. So now we're going to move on to looking at some of the algorithms. The first algorithm that we did was a basic word count algorithm. So to do this, we first split the XML data into chunks, as Noah mentioned, and then use NumPy to, or use general base Python to split the text, and then take the length and add that to a word counter. It was a little different for GPU and TPU as we tried optimizing those processing units using TensorFlow. So to do this, we used a tokenizer that would tokenize the white space, and then attempt to find the length of those chunks and add them to the word counter just like CPU. Next, we're going to look at the hashing algorithms. So with string hashing, the CPU, once again, was a simple algorithm using NumPy and also hashlib. And hashlib was used for all three algorithms, but the difference between the CPU and the GPU and TPU is that the GPU used the QP library, which uses CUDA drivers to configure the algorithm to run on a GPU. And the TPU used TensorFlow to configure the TPU for parallel processing. So lastly, we're going to take a look at the string language detection algorithm. And this algorithm used lang detect for all three algorithms. But once again, GPU used QP for to configure its many processors. And one note here is that the TPU attempted to use lang ID, but ultimately it was too slow working with TensorFlow, and so we ended up reverting back to using lang detect. Yeah, so those are our three algorithms.
All right, so now I'm going to go over the results a little bit. These are the results we got displayed with the speed up over the CPU on the y-axis and the algorithm used on the x-axis, all normalized against the CPU runtime. As you can see, the GPU and TPU usually got outperformed on the simpler algorithms, such as hashing and word count, but then when it came to the more computationally intensive ones, such as lang detect, we were able to realize a noticeable difference, and they were faster than the CPU. We did notice that this held true across both the 128 and 512 megabyte chunk sizes, just something that was kind of interesting to us. And then here on the table, these are the runtimes in seconds for the algorithms and architectures that we used. These are done on a portion of the data set, as we mentioned earlier, just because running the full data set would have been really expensive and just taken probably overnight. These show the same thing as the graph, just showing that on the simpler algorithms such as hashing and word count, it was slower to use the GPU and TPU in most cases, but then when we went to lang detect, it got faster for that. Just showing that the more computationally intensive ones were much faster with the GPU and TPU accelerators. And then on this table, we extrapolated the timing from the smaller data set and extrapolated that out to the full 96 gigabyte data set, and used the pricing that we could find online for the Google Cloud instances, namely 15 cents per hour for a 4-core CPU, 35 cents per hour for a GPU accelerated runtime, and $3.22 per hour for a TPU accelerated runtime. As expected, the CPU was the cheapest option just because, it was the least expensive per hour, and despite being slower than the others, it wasn't enough slower that the cost outweighed it. Yeah. And then kind of in conclusion, we found that given the correct circumstances, the TPU and GPU accelerated runtimes can provide noticeable improvements over a typical CPU runtime. But we did find that this was dependent on the algorithm being implemented and how computationally intensive it is, along with the size of the data. Both these factors we found led to the computation time eclipsing the time taken for data transfer and other optimization overhead, which again made the TPU and GPU worthwhile investments for those algorithms. In addition, based on the cost and runtimes, we found that even with the shorter runtime, in the best case, the TPU was still around 40 times more expensive to do the same algorithm run. And the GPU was just under 4 times more expensive for the exact same algorithm on the exact same data. And then finally, some future research that we propose is expanding the set and the scope of the algorithms, just to look into more deep learning neural networks and other stuff that would lend themselves better to GPUs and TPUs. In addition to possibly seeing how using larger chunks, maybe 1 or 2 gigabytes, see how that could affect the runtimes of the instances.